Hi, everyone. Thank you for bearing with us. I know you've gotten a lot of information thrown your way. Oh, we'll keep it interesting. We're talking about a little bit outside of, I think, what everyone's background is here is in infra. So we're going to look at AI inference from an infrastructure angle. At least I will, and hopefully you will join me on the journey. So inference infrastructure is still infrastructure. It actually looks oddly similar, or maybe not so oddly similar, but different domain. So the way that you can sort of think about the traditional database stack at a 30,000-foot view is a request comes in from the user application. It gets routed through a load balancer, a proxy of sorts. The purpose here is to obviously maximize utilization and prevent hotspots. And there's sometimes some sort of data placement that's involved. You want to maybe have sticky sessions so that similar requests from the same user or even across different users end up going to the same backend. On the inference side, it looks very similar, right? Instead of a query request, the API request may be, let's say for an LLM request, for the sake of example, we can say text in, text out. So text in on the request path gets routed through some sort of load balancer or proxy to a model provider where the actual LLM is hosted and the model needs to quote unquote reason through the request. In this case, you also want to maximize cache hit rates. It's something called prompt caching. And you might also want sticky sessions for maximizing cache hit rates so that as a user, as you communicate with your LLM backend, your requests go to the same model provider. So knowing this, we can dig into some of the performance and utilization problems that Samuel and I are going to look at with you today. Okay, so let's start with some terminology. Prefill and decode are the two stages of inference. Prefill is the first stage where your text in gets translated or interpreted in the model into tensors, or it's a bunch of mathematic operations. This process is extremely compute intensive. You need lots and lots of GPU processing units or similar to compute the mathematical equivalent or tensors, and that gets written to a transient state called KVCache. And that's kind of just like a writer in traditional database terminology. And then on the read side, basically after the prefill stage is done, decode is the one that takes these tensors and computes or reasons, quote unquote, to produce the text response. Again, assuming it's text in, text out. It could be other things like voice and pictures or video. But that's kind of the gist of it, where the decode side is very memory intensive. You are literally accessing the transient KV cache as fast as possible in order to produce the response. Okay, so let's look at the KV cache that I mentioned. In the very early days, it is indeed just a local transient state. You perform prefill, you produce this KV cache, and then the decode accesses it and produces the response. Of course, in a traditional distributed systems manner, every single component can be abstracted out. So what happens to the KV cache in its evolution? So we've actually come quite a long way in the past few years. Things happen really fast in AI, as all of you know. So we've passed the naive state, right? Which is you have a local state of KV cache. It started on the GPU itself, so next to the GPU, something like VRAM. With super high bandwidth, the GPU can just access this KV cache as a transient thing at, tens of terabytes a second, let's say. However, it's an expensive commodity. You might only get tens of gigabytes of VRAM next to the GPU. So then what do people do? They do local offloading. On the host itself, there's DRAM, which is the RAM that most of us know and have learned about. And of course, there is the NVMe disk tier. So as you move down the tiers, you get access to more memory. Of course, there's no free lunch. The trade-off is that the bandwidth goes down an order of magnitude every time you move down. So at the disk layer, you might be looking at gigabytes per second instead of terabytes per second. That's okay. So then over time, it matured to the second stage, where now you have cross-node access. Instead of just local node offloading, you can now maybe load balance a super hot node onto a second node so that that node can take some load. Well, what happens to the state that was on the first node? You have peer-to-peer sharing. Right, so now instead of accessing just my local disk, maybe I can access disk of a neighbor node who I'm trying to take some load off of it. So that's cool. Now you have a mesh of memory, and you can use it across nodes. However, there's still no durability here. If your instance dies, if your pod restarts, you lose everything, and you have to recompute the cache. So that kind of brings me to what we're going to dig into today, which is KVCache and that caching stateful layer as a first-class citizen, as persistent, durable storage that is remote to the host that we're talking about. It's remote to the host where the GPUs are physically located. So before I hand it off to Samuel, let's just look at the 3 layers that we talked about. So there's the very top layer of the application. This is where you talk about auth and security and kind of the gateway to your stack. And then you move down to the actual compute layer. Some of the most common open source engines that you might hear here are VLLM, SGLang, TensorRT is another popular one. Those 3 kind of dominate the market currently. And that's where the math that I talked about, that's kind of your service compute layer. And then what we're going to dig into is, of course, the database and the caching layer, which is the focus of the conference and the focus of our talk. That's where Momento operates. That's where LMCache and Tensormesh, where Samuel will talk to you guys a little more about the specific performance optimizations that we've done and collaborated on together at the KVCache access layer. So I will hand it off to Samuel.
All right. Thank you, Daniela, for the intro. And so I'm going to be talking about more of the performance optimizations now. And so to get rid of all the LLM jargon, I think there's only really 3 things you need to know about KVCache. The first is that it's produced on the GPU with a computationally heavy process. The second is that it can be reused across requests. For example, when you're using Claude Code, you send one request to Claude Code, and then the next request can reuse KVCache. Or another user who has a similar system prompt to you will have a reuse as well. And the third thing you need to know is that KVCache needs to come back to the GPU in order to be reused. So really what we do at Tensormesh and LMCache, which is an open source project for KVCache management, is we provide a memory hierarchy for KVCache. And one thing I am going to mention about KVCache is that it is a very large data structure. So the challenge is that when you have large-scale serving for LLMs, you have many, many users. And for example, if you have context lengths that go up to 1 million, which, for example, Claude Code now supports, that can be up to 20 gigabytes per user per request. So when you're serving users at scale, you have this massive amount of KVCache. And the GPU high bandwidth memory, or VRAM, is quite limited. For example, on modern data center GPUs, you only have 140 gigabytes per GPU, for example. So this tiered memory system is really important to utilize the CPU DRAM, to utilize the disk, and to utilize remote storage. Today, specifically, we're going to be talking about ValKey. And at the end of the day, the data needs to go from L2, which we'll call, for example, ValKey, back to L1 to DRAM, and then back to the GPU. And so the phase we're going to be looking at today is specifically from ValKey server to ValKey client. So this is one specific part of the movement of the data. And so the optimization metric we're going to be looking at is throughput. And this is quite specific because KVCache is a particular kind of data where all of it needs to land back on the GPU before computation begins again. It's not like, for example, video streaming, where you could have some of your data come and you could render a blurry image for a while. You need all of the KVCache for all of your tokens to arrive before you can begin any inference. So we're really looking at tail latency here and not just regular latency, so P99 latency. And today we're going to be looking at a journey of improving the throughput of the ValKey client and server. And lastly, the 3 operations that we really are only going to look at are lookup, retrieve, and store. So really get, set, and exist in the RESP protocol. And the retrieve is the most important because that's on the hot path of the LM inference, but the store is less important because it can be done asynchronously. And so to start out, we tried to just use some clients that currently exist. So this is a connection object from Redis Pi. And this looks innocuous, but actually something weird is happening here where you can see that a KV bytes object is being returned. And what that means is that under the hood, the client is forcing you to create a copy of your data. You're not able to pass in a buffer and have the client fill it in, but the client's going to create an extra buffer under the hood and give that back to you. And so this is a kind of first indication that this client is quite suboptimal. And so we start with a throughput of 0.3 gigabytes per second. And sorry, just to go back to this graph, I didn't explain it at all, I just realized. So another very, I guess, fundamental thing is that the computation of KVCache, if you think about, without going into jargon, attention is basically matrix multiplication, and its complexity is O of n squared. So those curves are for modern data center GPUs. For example, the red curve is an A100 from NVIDIA. That's from around 3 years ago. The blue and purple, those are B200 and H100, which are GPUs from the last 2 years. But loading data transfer is linear. So the longer your context is, the better it is to load KVCache. So the whole problem statement is that there's a race. When a request arrives, you have two choices. You can either recompute the KVCache, which you've probably seen a lot of the context for this request already, or you can try to load it. And if you can't load it faster than you can recompute it, then there's no point in accelerating. But there still is the benefit that you use less GPU cycles to recompute. And GPU cycles basically corresponds to the number of GPUs you need in your inference stack. So the number we're looking for is around 2 gigabytes per second, just kind of taking that out of a black box. If we have 2 gigabytes per second throughput here, we're pretty good to accelerate inference. And so now I'm going to be talking about, oh, yes. Yes, the loading is the dotted lines. They're quite light. So here, for example, that's 0.5 gigabytes per second. This is 2 gigabytes per second. Sorry. So the vertical is delay, and so if you have 2 gigabytes per second, you can outrun pretty much every GPU. So your delay is lower. Yeah. Thanks for the question. And so the first optimization that we did was to get rid of these copies. And so to do that, we implemented the RESP protocol ourselves, which was relatively easy because we didn't need most of the features. We just needed get, set, and exists. And so we just did some scatter gathered for the sending, so you can have non-contiguous buffers be sent across the your socket. And then we just used receive into, which is pretty native. And so this already gives 6.6 times improvement. We already hit our SLO, which is 2 gigabytes per second. And just for some context, in LMCache, there's multiple storage backends, and some similar optimizations we've done is when you do disk offloading, you want to use O direct to skip the page buffer. And then when you, for example, use S3 as a client, you can do a similar optimization using dev SHM, which is a RAM file system. And you can use mmap, so multiple processes don't create more copies. And then the second optimization that we did is a little more specific to this workload, which is that when a request comes in, you have a long tensor of tokens. And the way that we store the objects in the database is by cutting up this tensor along the token dimension into evenly sized chunks. And so usually a request won't come in as a perfect multiple of the chunk size that you have. So here at the end, there's a little 23 remainder after dividing by 256. And so this also, again, looks like a small detail, but if you do a simple optimization of not storing the very last little tail, what you can do is avoid having to store metadata. Because, for example, if you have unevenly sized chunks, you have to first query how large is my data, and then you can allocate a buffer, and then you can load it in. But if you can a priori know that all of your data is the exact same size, then first of all, you don't have to store metadata, so that's half the reads and writes. And secondly, you can do a little trick when you're parsing, which is you can read the header, and then you can just blindly read all of the KVCache with your pre-known buffer size, and then you can just kind of validate the trailer in the REST protocol, which is CLRF. So this brought us from 2 to around 4 to 5 gigabytes per second. And so this is already way past what we're at, but because we're still working in Python, there's definitely room for improvement. So why are we working in Python? It's not the best performance language, just because the ML ecosystem is all in Python. PyTorch, VLM, SGLang, all these serving engines. So LMCache is also a project in Python. But as many of you know, Python has a global interpreter lock, which means that two threads can't actually run simultaneously on multiple cores. And this usually shouldn't matter for workloads that are I/O bound, such as a lot of data reading and writing. But what we found is that this actually does have an impact on our workload. So this is a very kind of hard to read flame graph, but this is 8 threads simultaneously doing reads and writes. And the lines are showing that basically one completion, the green is the work, and then the purple is kind of the space that is empty for the thread, is that one completion can only start after another one ends. And that's because of Python's global interpreter lock. And then some other profiling work that we did, this is another kind of hard to read flame graph, is that if you submit multiple coroutines to Python's event loop, you actually don't know when the event loop will schedule your coroutines. So for example, here again, the green is the actual coroutines doing work, and the circled is the little gap. So you batch submit coroutines to Python's event loop, and then it decides to do some other work for other processes or other threads. And that ends up delaying your overall computation finish. And so if you just submit one coroutine, then there's no gaps. So what we decided to do to get rid of Python's global interpreter lock is to lower ourselves into C++ and then to have all of our operations be batched. So as mentioned in the beginning, KVCache is a particular type of workload where you need all of your data objects to arrive before your computation can begin. So it's very safe to say all of our operations can be completely batched. And the way we divide the work is every request, all the threads will work on it. The sort of more naive way is to have one thread work on one request, but there's no guarantee that the number of requests consistently exceeds the number of threads. And the submission model we did is very similar to IO Uring, which is part of the Linux interface for batching multiple files, reads and writes, which is that we create a submission queue. So all of the batched operations look like a single submission event on the Python side, and then we immediately release the GIL. And then when all of the batched operations have finished, we are notified on the Python side through another interface in Linux called eventfd, which allows a process to subscribe to it, and the kernel is responsible for waking the process up when the file is written to, which the C++ side is responsible for doing. And so to summarize this short list of optimizations that was done, hopefully these were presented from a more systems perspective, even though this was a LLM-specific workload. We started at 0.3 gigabytes per second. Removing user space copies gets us to 2. Size invariant workload gets us to 5. And then at the end, getting rid of Python's global interpreter locks gets us to around 10. And so feel free to check out this open source project. There's a lot of low-level systems optimizations, a lot of interesting systems work, even though it is an ML project. I think it's kind of at the intersection of ML and systems. So, yeah.
Thank you.
Awesome.